5.2, Riemann integrals. Riemann. Riemann integrals. Okay. So, we have this way of defining the area, right? And we, there was something a bit arbitrary about it, right? In that we took this partition and then we sampled the function at the right endpoint and we multiplied, blah blah blah. What was arbitrary about it was the choice of sample point, right? Like what happens if you take some other sample point? Why did we define the area using the right endpoint rather than any other point? Okay, so there's something a bit arbitrary about it, and so we're gonna the way one defines the integral is deals with that arbitrariness. Okay, but so in order to define the integral, we're gonna basically take the right endpoint approximation and then make some sort of more general sort of notion that encompasses that. Okay, and then we'll use that to define the define the integral. Okay, so here's the first idea, and it's something called a Riemann sum of a function. Right. So you have some function f on AB to R. So Riemann sum of a function f based on a partition x naught through xn. X naught is A, xn is B. Okay. So the idea is like this. The idea is like this. You have some function, right? So you have your function on AB R. 2, you have a uniform partition of AB into n parts. So the same as we had yesterday, right? You divide A, B into n intervals, each of length b minus a over n, right? Okay. And the third thing you have is you have a choice of points. S1 to Sn, okay, where Si lies in xi minus 1, xi, the ith interval. Okay, so the picture is like this, right? You have your function on AB. Right? You divided it into equal parts. X naught, x1, xn. Right, and then in each interval, you take a sample. You choose a point. Okay, S1, S2, S3, S4, S5, S6, blah blah blah. So this is going to be S of n, right? Okay, and then sorry, let me notate this thing. The choice of points I'm going to denote by capital S sub n. Okay, so that's your choice of what we call sample points. It's just these points. Okay. And so when we'll use this capital R at S of n. By this we mean the summation f is I delta x and I equals 1 to n. so it's a number, right? Right? This thing is some number that you get by taking the function and evaluating it at the sample point. Right? So you evaluate the function at the sample point, right? And you multiply that thing by the width of the interval. Sample point, width of interval, sample point, width of interval. Right? So geometrically, what you're doing is getting the sum of the sum of the areas of these rectangles. Okay? Right? And this thing is called the Riemann sum of f based on Sn. Based on this choice. This is the Riemann sum of f on AB based on this choice of sample points. Okay, so you see, what's the difference between this and the right endpoint approximation? This is basically the same thing as the right endpoint approximation, except for the right endpoint approximation, we take our SI if. So notice if we take each SI to be XI, then this is the nth right endpoint approximation. This is the nth right endpoint approximation. So each of the right endpoint approximations is a Riemann sum, right? So each such is a Riemann sum. Each of those guys is a Riemann sum. Right. Okay. So, but you can do other things, right? So you could, for example, you can sample basically however you feel like. So, for example, if I take the sine function, and I take a Riemann sum based on partitioning the base into two parts, right? So I'm going to split it into two parts, right? Then you can choose your sample points as you like. So if I say pi is one sample point, and then 3 pi over 2 is another sample point. Okay. So in that case, I get pi times delta x. So f of pi delta x, f of 3 pi over 2 times delta x. Right? So that's going to be 0 times pi plus -1 times pi. Okay. So that gives me -pi, right? -pi, and so that's the Riemann sum, for this integral, right? So this is a Riemann sum. For this function, right? But I could have chosen some other way, right? I could have chosen, say, the first sample point to be pi over 2, and the second one to be pi, say. And that would give me pi, right? And so that's another. This is also a Riemann sum. Okay. Yeah.
How do you know when to use Riemann sum versus whatever?
Right endpoint approximation?
Yes.
Like,
would it tell you in the problem, or do you just have to intuitively figure it out somehow? Is there a way?
Well, so what we're going to do is see that basically the way we're going to define the integral is in terms of the Riemann sums, and you'll see that it's basically up to you what Riemann sum you want to use. So if you want to use right endpoint, if you want to choose the right endpoints always, the question will be answered shortly.
Okay.
It's good.
So what if the question asks for, well, so obviously when it's an integral, if it is on the, like, if it's negative, if y is negative, then you will subtract it from the overall area that you got from the positive Riemann
Right,
sum.
because you get a negative number times the width. Yeah.
Correct. But what if it asks you for the total area? Don't you keep it positive?
Yeah. So in that case, you calculate each of these things, and you'd say over here I'm going to take so that would basically amount to taking the absolute value of the value.
Okay.
Right. Rachel.
Aren't some of the choices of you say you can choose any sample points you want, but wouldn't some of them be a lot more accurate?
Yeah. So
That one you just did there is not super accurate.
Right. So this is so here in the first one, what we did was basically approximate this thing by taking this box, right? And then the first box was of 0 height. In the second one, I took what we're basically doing was taking this box, and then the second box was flat, right? Okay. So what we're saying is that there are these things called Riemann sums. Okay. Certainly, they're not they're more or less accurate. Yeah, some are more accurate than others. Okay. Let me just make one comment. There's something called an upper Riemann sum. We're not going to really deal with these guys, but there's something called an upper Riemann sum and a lower Riemann sum that I should at least tell you about. And what those are if you have your function and you take your partition, the upper Riemann sum, what you do is you say, well, I'm going to take the maximum height in each. My sample point will be chosen to maximize the height. Okay, so here I'm going to take the one that I'm going to take here. In this one, it looks like I'll take one somewhere in the middle. So here's my first sample point, here's my second. Right. In the third, clearly I'm going to take the left endpoint. In the fourth, clearly I'm going to take the right endpoint as my sample point. Right, here I'm going to do this. And you see, that thing would be what's called an upper Riemann sum. So upper Riemann sum, one chooses the maximum as the sample points. And the lower Riemann sum, well, you take the minimum. You take the places where it's the minimum. So here I take 0, et cetera, et cetera. You know what you can see. Okay? Another remark is that clearly the sum, the value, depends considerably on the choice of sample points. Okay. And let me give you one pathological example. So this is example 1 here. Example 2. We look at the function which is 1 if x is rational, and 0 if x is irrational. Okay. And let's look at 0, 1. Okay, so it's 1 on every rational point and 0 on every irrational point. Okay, and let's suppose we divide this thing into 10 parts. We divide the base into 10 parts. Then what kind of Riemann sums? What can you get? What are possible Riemann sums that you get out of this? Well, if in my first one, suppose I choose all irrational points, then what's my sum going to be? Suppose I choose all my sample points to be irrational, then what am I going to get? 0, right? Because I'm going to get f of an irrational point, f of x1, delta x is 1/10, f of x2, is 1/10, blah, 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 f of x10 is 1/10. And all these, if all these guys are irrational, then I get 0, right? And if I choose only rational points, right, then I'm going to get what? I'll get 1, right? I'll get 1 because I'll be taking, type 1 and everything, and I just get this, just get the square, right? The unit square, the area of the unit square, right? Okay. If I choose some mix, if I choose like three rational and 7 irrational, then I'm going to get 3/10, right? If I chose 7 rational and 3 irrational, I get, right? I get 7/10, etc., etc. Okay. So and you notice, so in that case, the Riemann sums are pretty wild, right? The Riemann sums are pretty wild. Like I can get basically any number I feel like. Anything between 0, well, I can get I can get numbers between 0 and 1, whatever number I can get, this whole range of numbers between 0 and 1. And even if I take a really fine, suppose I divide this into 1,000,000 places, right? Okay. Does that constrain the values of the Riemann sum? Not really, right? Because I could still take all zeros, right? I could still take all irrationals and get 0, and I could still take all rationals and get 1, and I could still take a combination. In fact, I can get basically, more. I've got more numbers to choose from now, right? I can choose right? I can get all sorts of numbers. So, right? Even if I take this, take 1 billion here, still the Riemann sums are very wild, okay? Because if choice of sample points is free, you can get all sorts of numbers out of
But
this.
it'll approach isn't it true that it'll approach like a more finite number, like a number closer to what the actual area is?
No, because
Wouldn't it have to be in between 0 and 1?
it will
Yeah.
be between 0 and 1, certainly. Yeah, but still, you can get basically anything between 0 and 1. Right. It's not as I'm refining the partition down here, the numbers don't seem to be any more controlled. Right.
Oh, are you saying like you're picking one? Like, is that what it is?
I'm saying that if you suppose I divide this thing into 1 billion
Like rectangles.
intervals. Okay.
Okay.
Divide this thing into 1 billion intervals. Okay. And you go into a room, and your friend goes into a room, and you're allowed to choose your sample points as however you feel like. And your friend is allowed to choose your sample points, her sample points as however she feels like. Are you going to come up with the same number?
No.
No, very much no, right?
No.
Are you going to be even close to each other? Well, I mean, both of you will be between 0 and 1, but there's nothing that says your numbers are going to be close to each other,
No.
right? Because if you went in your room and you said, I like all rational numbers, you would have gotten 1, and your friend would have come out liking irrational numbers, your friend would have come out with a 0, right? So no matter how fine you take this thing, still there's no control over, there's nothing that says you're going to end up with numbers that are close to each other. Okay, so, okay. So here's the definition. So we basically, what happens is we don't want to think about these sorts of functions. Okay, we don't want to think about functions like this. We want functions that behave more nicely. That the functions for which, if you take finer partitions, then the Riemann sums are forced to tend to some limit. Okay, so we're actually going to exclude. The next definition will be used to exclude this possibility. So here we go. This is the important definition. If the limit of the Riemann sums as n goes to infinity exists independently of choice of sample points, independent of choice of sample points, then we call f an integrable function. On AB, and we write this equals, let's say, and we write that this thing equals L. The way you read this is saying the definite integral of f on AB equals L. Okay, so so this for this function, this is not an integrable function. I guess you guys just keep on reading. I'll just. Yeah, Richard. Yeah.
So if basically the definite integral is the limit of the Riemann sum,
Mm-hmm.
I mean, and it's as like basically the intervals is approaching infinity. Like based on what we discussed before, wouldn't that just make it more like, wouldn't you have more variation if you had more intervals?
So this definition says we're going to call a function integrable if, when the partition becomes finer and finer, the Riemann sums are forced to tend to some limit. Okay. So, for example, in this one, as our partitions got finer and finer, the Riemann sums did not tend to a limit. Okay. So this function is not. This f is not integrable.
Oh, that was an example of something that's not integrable.
Yeah, this guy is not integrable. Okay. Okay. So we're only going to be dealing with integrable functions. When talking about the integral, we only can deal with things that are integrable. Okay. This one isn't integrable. It is integrable in a different sense. So there's another sense, something called Lebesgue integration. This function is integrable in the sense of Lebesgue, but it's not integrable in the Riemann sense. And so we're not going to consider it. Okay.
But for all of the functions, it will tend towards a number of.
Well, not for all the functions. Not for all the
Integral.
functions. For some functions. Okay. For some functions, and for that, we have this theorem: if f is continuous on AB, then in fact it is integrable. So if your functions are continuous, then this is going to work out for us. Okay, then the Riemann sums are going to tend to some limit. Okay, and we'll call that limit, the definite integral on the thing. Okay. So right. So although at the beginning when we chose our Riemann sums for the sign, it looked like you could get very different things. The fact is that this is a continuous function, and as you refine your partition, no matter what choices you make, if you let the partition become infinitely fine, you and your friend are going to end up with the same limit. Right? You go into a room, your friend goes into a room and says, you're allowed to choose however you feel like, but we're going to see what happens when we let the partition become infinitely fine. Right? No matter what, your friend's going to come out and say, I got 0. And you're going to come out and you're going to say, well, the limit was 0. Okay. So even no matter how you chose your things. Okay. Okay. So right. So the point is that for continuous functions, one can calculate this thing as the limit of Riemann sums as n goes to infinity. Okay. And what this says is that you can make whatever choices you like. For these guys, you can make whatever choices you like, and you're going to end up with the right number. Okay. It's not like you're going to, based on your choice, you get different numbers. No matter what choices you make, as long as you let n go to infinity, you're going to tend towards the right number. So notice that this is in general a pain, right? Because how do you calculate the integral? Well, you have to take a Riemann sum. You have to take Riemann sums for every n. Take the Riemann sums, choose your points, calculate it, and then let n go to infinity, right? We can do it. We did it last time. Right? We did it for a right endpoint, but it was not fun. Well, it was. I don't know if it's not fun. Maybe it was sort of fun. It wasn't fun. In any case, fortunately, we don't have to do this. Run through this process every time, thanks to the fundamental theorem of calculus. Fundamental theorem of calculus number 2. Okay.
What was the first one?
This is always called fundamental theorem of calculus number 2. But we're going to introduce it first. Okay. It's this: f continuous on AB, and big F, any antiderivative of little f on AB. Then the definite integral is going to be the difference of the antiderivative at the endpoints. And this is the thing that we mentioned at the end last time. Okay. So, for example, if I say, what's the antiderivative of 1 over x between 1 and e? So here's 1, here's e, and here's the function 1 over x. And I'd like to know the antiderivative here. I'd like to know the area under the curve here, right? You say, okay, all I need to do is take an antiderivative of 1 over x. What's an antiderivative of 1 over x?
Natural log.
Natural log, right? So you take the natural log between 1 and e, and you say, well, this is going to be natural log e minus natural log of 1, right? So that's going to be 1 minus 0. So the area is 1. This thing here means you take this function, you evaluate it here, and subtract off the value of the function here. Okay, so it's just a notation for the difference at these 2 points.
We can ignore the c we usually add because it would cancel out in the last step.
That's right. Although, I mean, you could throw in the c if you feel like. You can use any antiderivative. Right. And so the theorem says choose any one you like. And you're right, if you choose a different one, it will differ by c, which will be subtracted off anyway, which will cancel out anyway. Okay. There's another one. So the definite integral of secant tangent from 0 to pi over 3. Does anyone know the integral of secant tangent?
It's secant. No. Tangent.
It's secant.
It's a secant. Yeah. It's a secant.
Oh,
That's okay. You were right the first time. Right. So you take the secant between these 2 points.
Oh, it's secant square.
Yeah. Tangent's derivative of secant square. Okay. So whatever. So you see that. Okay. So the point is that integration becomes easy, right? You don't have to run through run through taking, you don't have to take Riemann sums and then the limits of Riemann sums. All you need to do is find an antiderivative and then take the difference of the inputs. Okay. Sometimes it won't work, right? Sometimes, like if somebody says, what's the definite integral of e to the x squared, you'd have to find an antiderivative of e to the x squared. Does anyone know an antiderivative of e to the x squared? Actually, there is none that can be written down in closed form. So don't worry, you can't. Don't try it.
That was on the homework, by the way. That was on the homework.
No.
It was a problem.
Okay, so, but
That
But,
can't be
hold on.
differentiated.
it can't. It could not have been a problem where you needed to find the antiderivative of this because that's impossible.
No, it was
It may
x,
have been
it
a
was
pro-
x times.
It may have been a problem where you were asked to find a Riemann, right endpoint approximation of it. That's fine. Okay. So for something like this, if you wanted to find the area, you'd have to go through the process. Okay. Okay. So next time we'll talk about why this is true, right? Why does this happen? Is this some sort of miracle, right? It saves you from doing Riemann sums.